In this video, we're talking about approximating derivatives using tables. So a quick review. All right, we learned about the derivative. It's the instantaneous rate of change, which could be approximated by average rate of change. So in our formulas, we have the average rate of change formula, which is some y values, some outputs on the top, and some x values on the bottom. All right, we're not going to use these specific formulas in this video, but basically the idea that average rate of change, as we get closer to our desired value, the average rate of change approximates or gets close to the actual instantaneous rate of change that we care about. All right, so let's look at this example. I'm going to use this table. We're going to approximate f prime of 3. We're not going to know exactly what f prime of 3 is, but we can get as close as possible with this table. All right, so the basic idea is we're looking at our function. We can start with an average rate of change between these two values. I'd say we care about this red value. But we're going to get closer and closer, and the closer we get to our point, all right, with our two things for average rate of change, the more accurate our average rate of change is going to approximate the instantaneous rate of change. So basically the idea is get as close as possible to the number you care about. And if I look at my table, where are the numbers that are close as possible? They're right here in the middle. So if I found this average rate of change between these two values, it'll approximate the derivative at 3, the instantaneous rate of change. So I'm just going to do my y values on the top. All right, just like I'm doing a normal slope, all right, because it's the slope of the secant line. My x values on the bottom. And these are not super nice decimals, so I'm just going to use a calculator. 9.0601, 8.9. Oops. All right, so the top ends up being 0.12, and the bottom is 0.02. And if I divide those, I get 0.6. So the best approximation I can get for the average rate of change of this function is 0.6, which would be 3/5, if we want to write it as like a slope where we have rise over run. All right, but this is the basic idea of approximating your derivative. Just pick the values that are closest. All right, so in this case, they're not like super close decimals, but again, we can do as best we can of approximating the derivative by just putting values close to 1. I try to be a little tricky here because the values close to 1 are not in the middle of the table. They're actually 0 and 2, which are slightly to the right. But that's not going to change anything in practice. The slope of the secant line, which is going to approximate my derivative, is the y values on the top and the difference of the x values on the bottom. And I get 1/2. So again, it might not be the exact derivative, the exact slope of the tangent line at 1, but that's the best approximation I can give with this table. All right, here's one for you to try on your own. All right, approximate f prime of 2. All right, I'll show you the answers to that in 3, 2, 1. All right, so for this one, you actually have kind of a choice to make. You want to be as close to 2 as possible. So you could pick 2. Well, we want to be at 2, so we probably pick 2 as one of our values. We pick the number that's just below 2, 1.5, and we get 9.2 as an approximation of our tangent line. Or we could pick 2 and 2.5, the number that's just bigger than 2, and we get 15.2 for our approximation of the slope of the tangent line. So if you had these values and you knew, like, if I go just below 2, I get 9.2, just above 2, I get 15.2, what would you do? Well, if you kind of average them out somewhere in the middle, maybe you get like 12.8 or something like that. So we're not going to get an exact value of the derivative, but kind of using these to kind of influence or kind of help you approximate the derivative. These are fine answers themselves, but if you kind of think about it having lower on one side and higher on the other side, chances are it's in the middle. All right, so here's the important things from this lesson. Remember that average rate of change can approximate the instantaneous rate of change. So doing these two values will help you get with the instantaneous rate of change. And just remember to use the values closest to your desired value. There's no point in, if I care about this value, using a value over here and here. I want to be as close as possible to approximate that instantaneous rate of change.